Okay. Ah sì, certo, se non collego questo. Okay, there you go. Okay, yes, I wanted to add something which came up from a discussion I had with some of you. Okay, so, oops, sorry. So we have an area, we have obstacles in between. And at the moment, we have investigated this these combinatorial approaches, means that we find a kind of a roadmap that connects all the different points in the diagram, or at least a representative set of these points. Okay. And then the idea there is that wherever you are, suppose you are here, you move to the closest point in the roadmap. Then you follow the roadmap with dikes or whatever you want. When you arrive in the proximity of your goal, you just get out from the node, you carry out a final maneuver, right? But one of the problems that came up in the discussion is that at the moment we have considered a geometric graph, polyline essentially. So we simply draw these lines, straight lines, and we associate a path with a sequence of straight lines like this. These straight lines are, of course, guaranteed to be collision-free. But once you move with your vehicle, what saves me from saying, okay, maybe the vehicle does something like this to follow the path, and then it crashes somewhere on the boundaries or on the external boundaries of the map or on the external boundaries of an obstacle. This is a possibility. Okay, so you have two options here. The first is that when you do the planning, you already reason in terms of Dubin's maneuvers. So whenever you reach a point in the graph, the point is actually not only associated with X and Y, but also with a different orientation. So you can consider 4 orientation, pi fourth, pi alpha, 3 pi fourth, etc., etc. You consider a point, and then you have a few orientation with which you may arrive on a point like this. You restrict the number of orientations, so your graph is actually a multi-graph, is layered. It's like in any position you have X, Y, but you can have multiple other nodes on top of that because you have to sample in another direction, which is in this case the different pose of the robot. Okay, and then you can create your graph and connect all of these nodes by already reasoning in terms of Dubin's maneuvers, and find out which nodes is actually connectable to each other. So you create a much larger graph structure in which you have also this information on the orientation of the robot when it gets to one of these points. So each point is actually like a multi-layered point, one for each orientation. And then in this case, you can, while you are constructing the roadmap, directly consider the Dubin's maneuvers that the maneuvers that join all these different nodes. And this is a possibility. The other possibility is that you just leave with a geometric decomposition like this, okay? And then you leave enough room around your edges so that there is space for maneuvering, like here, right? If you have to depart from the trajectory, you have some margins in which you can maneuver without touching the obstacles, okay? And this can be done in two ways. One is by inflating the obstacles a little bit more, okay, so that you are artificially restricting the accessible space, okay, by considering a larger shape of the obstacles than needed. You already are supposed to do this because there is anyway a localization error to account for, right, while you're moving. Or I would say you can use an approach like the ones that we are seeing, which is this maximum clearance. Because this maximum clearance is a solution that finds the path in the middle of the obstacles that stays as away as possible from the obstacles, right? So you want to have the maximum clearance on the left and on the right. So if even in this case you don't have a space for maneuvering, then there is little hope that you can have it anyway, right? Because it means that there are some areas of the map where the spaces are so narrow that you cannot realistically maneuver there. Okay, so considering a maximum clearance map has two main advantages. One is that it gives you more robustness with respect to localization error. It allows you to have sufficiently margin to avoid collisions. And the other is that when you move from the geometric planning to the actual kinematic planning, you have some margins to maneuver around the trajectory and stay within these boundaries. Okay, so this is typically a very conservative solution that is recommendable for this. So the last thing we said is, I repeat, what is a Voronoi diagram. And in this case, as I said, if you just have got 2 points like this, okay, the way to, and these points represents the obstacles you want to avoid, the obvious thing to do is to stay right in the middle, which I didn't do now. Okay, okay, let me fix this. Suppose that the other point is roughly here. Okay, so you take the line joining the 2 points, you can see a perpendicular to this line, and this is the locus of all the points that have equal distance from these 2 obstacles. Okay, if you have more than 2, you can suppose you have 4 points, you have to reason pairwise. So you can draw a line for this, another line for this, okay, and so on and so forth. And in each point, you consider the points that are the closest, and you refer to that line. And therefore, you come up with something, with a cobweb like this, that I'm showing here, which is called the Voronoi diagram. Okay, so if you use a Voronoi diagram, you have a guarantee that you will stay away from the obstacles. Okay. Now, and as much as possible. Now, but you say, okay, but my problem is the obstacles are not pointwise. They are more complex. And so what can I do? Okay, suppose you put yourself in a condition where you've got a corridor, right? So your obstacles in this case are the two boundaries of the corridor, right? And you want to stay away from these as much as possible. Even in this case, it's possible to reason, right? So if you take any point like this, okay, this point is closer to one of the obstacles than to the other. So of course, it doesn't belong to the maximum clearance map because you have an unbalanced situation, right? So the obvious, so in this case, the closest point to this, the closest point of the obstacle to this is just this. And you have one. If you stay here, again, you have just one closest point in the obstacle to your point. If you stay in the middle like this, you have got 2 points that are closest to you. Okay, so the cardinality of the set of the points that are closest to you grows. This is what's happening. Okay. Okay. And this can be used as a rationale to define more precisely what we mean by maximum clearance and by generalized Voronoi diagrams. Here we have a definition. So suppose we have our space with obstacle in the middle. Okay. Another obstacle here. Okay, then you say, I consider beta as the boundary of C3. The boundary of C3 is, in this case, given by this, right? This, this, then this part here, and this part here. Okay, now the pen is too thick, but I mean the borders of the obstacles. Okay, so if you define now a distance d, which is the typical Euclidean distance between the 2 points, so it's the norm of the difference of the vectors. So for every point in a configuration free space, you can define as a clearance as the points that belongs to the boundary, okay, the boundary of your obstacles, so of your free space, because they are the same. You can see them as boundaries of the obstacles or of the free space, and so they are different here, okay? Which is the closest to your point. So if you have a situation, oops. If you have a situation like this, I take this, I take this point here. If this is P, Q is the closest point, and this is Q, right? You go around, you travel around the frontiers of your obstacle, you find the point which are at the minimum possible distance from Q. Now, there are cases in which these points can be more than one. Okay, so suppose you are right in the middle between these two obstacles. Okay, in this case, this distance and this distance, suppose they are equal. Okay, I mean this distance here and this distance here are equal, right? So if you stay right in the middle, you have 2 points belonging to the frontier of C3 that are at minimum distance from the point that you are considering. Okay, so you can you can give this a name, and you can say that near is the set of all the points such that the distance from a point P, from a point Q, so I reversed P and Q, sorry, from the point Q is equal to the clearance. Okay? So in this case, okay, you have to invert. This is Q and this is P. In this case, there is 1 point. In this case here, there are 2 points, right? If Q is this point. Okay? And now, if you introduce this definition, then you can give an exact definition of what a Voronoi, generalized Voronoi diagram is. And it's defined as the portion of C3, okay, the area, the subset of C3, such that it's near, for each point belonging to this set, it's set near, the set made of the point that are at clearance distance from this point has a cardinality greater than 1, sorry. Okay, so if you are considering again 2 lines like this, and this is the boundaries of your obstacles, and you consider this point here, in this case you have a unique point, which is at the clearance distance from you, right? So in this case, this point doesn't belong to the Voronoi diagram, to the generalized Voronoi diagram. If, on the contrary, you move exactly in the middle between the 2 lines, then you have got 2 points. So the cardinality of the set near becomes greater than 1, and you can say that this actually belongs to the Voronoi diagram. Is it clear? Okay. And this is an exact definition, right, of the Voronoi diagram. Okay, now we have essentially 2 conditions. A condition point, and in this case, the Voronoi diagram is made, as we already said, of the line that travels in the middle between the 2. So you have to join the 2 points and consider the orthogonal line passing exactly in the middle of this. And this is the Voronoi diagram, the piece of Voronoi diagram in this case. Then if you have got 2 edges like this and this, what is the Voronoi diagram? It's the bisector, because the bisector is defined as the root, as the locus such that of the points such that the distance between the 2 sides, in this case they are the 2 edges delimiting your angle, is equal. Okay, so by definition, all the points along the bisector, okay, belong to the Voronoi diagram. Okay. A more difficult, less obvious condition is one that happens when you have got a point like this and an edge. Why is this more difficult? Because in this case, you have to go back to your old geometry books and find out that the locus of points such that their distance from a point and from a line is equal is the parabola. And this is called focus of the parabola, right? And the line, I don't remember how it's called. So when I studied it, it was in the high school, so some time ago, right? But anyway, if you take a straight line and a point, the locus of the points, such that the distance from the line and from this point is equal, is the parabola, which is focused in this point. Okay? This is the definition. Okay. So if we leave these definitions, okay, we are able to construct the minimum clearance map for any type of map. Consider in this case, okay, let's start from this, okay? Here we have different situations. Now, if you consider the situation which is above this point, the closest points of the frontier of the obstacles are, on the one hand, the edge of this guy, and on the other hand, the edge of this guy. So in this area that I sketched here, okay, the piece of the Voronoi diagram is a line like this, the bisector of this angle. Okay. Likewise, if you move farther enough from this point, you have here another situation, edge. In this area in between, the closest point that you can find in the OBS area are the vertex that is associated with this two edges and this line here. Okay, and therefore the piece of the Voronoi diagram is this piece of parabola. Okay, so in essence, our generalized Voronoi diagram will be built by pieces of lines and arcs of a parabola that have to be connected with one another. Is it clear? Okay. And this is the situation in a real case, you see. Let's consider this piece from instance. Oops. This piece here, from here to here, we have this bisector because in this area, the points of C-ops, which are the closest to your point, are actually these two sides. So you have to consider this guy and this guy, right? And so you take a piece of bisector. Okay? Then here you can have another area, for instance, this one, in which you have to consider this point and this guy here. And then you have a piece of parabola. Then in this area here, you have to consider this and this. And therefore you have a straight line and so on and so forth, right? And you can construct this generalized Voronoi diagram in this way. Okay, but anyway, if you Google it, you will find the exact algorithm. I have just explained how it works. And this is an example. Now, there is an algorithm for doing this, which is called the sweep line method. And it can be shown that if n is the number of vertices on beta, the complexity of the best algorithm known to construct the generalized Voronoi diagram is n log n. And the algorithm is called the sweep line. Okay. I have a good news for affectionate C++ programmer. There is a wonderful library in Boost that does exactly this job for you. Okay? So you can simply download it and try it out. But now, this gives me the opportunity to speak a little bit about this point. For your project, you are not supposed to rediscover the wheel. So if you have a very good library, like in this case, or like in the clipping library that we have seen for obstacles, etc., just go for it. Okay? I am, in this case, your employer. Okay? So I don't want to test your ability to write an algorithm from the ground up. I want you to find a solution. But the solution has to be well thought and well studied. So it means that you have to evaluate different alternatives. You have to make something like a preliminary complexity evaluation given the problem at hand, if it's convenient to go one way or the other, right? So for me, it's not sufficient that you just use one algorithm. And what is the rationale? Okay, the rationale is that this is not what you would do in a real world scenario. But from my point of view, you are not allowed. We will see many techniques. Some we already have seen, some more we will see. But you are not allowed to just pick one because you like it or because it looks simple and then turn off your brain and just go for it. No, because when we do the oral examination, when I will read your report, I want to see concrete pieces of evidence that motivate one choice or the other. And you have to be able to defend your choice and make the case for your choice. And therefore, you have to show me familiarity with all the topics that we are covering in this course. Okay? This is because all of them in different circumstances could be needed. Okay? Because once you have this in mind, clearly you can look around, you can decide that this algorithm is fine, I can use this library, I will rewrite my own piece of library for any reason. Okay, you can do whatever you want, but whatever you do, you have to motivate. Okay? So even if you, on the contrary, you decide not to use this and to re-implement the maximum clearance algorithm from the beginning, okay, I can understand that you do it for your personal pleasure. Some people like to play video game, other people like to implement algorithms. Some people like both, okay? And many in this room perhaps like both. But the key point is that even in this case, you have to suggest, to give me, it's not sufficient and I say, okay, I implemented this myself, I deserve more. Okay, you deserve more if your algorithm is at least as good as the other you find on the internet. You see what I mean, right? Or if it solves, at least if you say, I wanted to study the problem myself of how to implement this because I didn't like the data structures used by this algorithm, I preferred other things, etc. Or you say, I don't want to use Boost because Boost is something outdated, I will go for other types of libraries. Okay, be my guest, but you have to show me that you behave at least as well as this, in this case, right? Because otherwise, as your employer, I say, but you're crazy? You wasted the time I pay for just to play? No, no way, okay? I'm kidding, but not too much. Okay, now let's go back to the triangulation and, sorry, not triangulation. It's a kind of like the triangulation case. This is called shortest path design. By the way, if you want to find more information on each of these things, there is a book of Laval. It's this thick, but more importantly, its PDF is available on the net, so you can download it freely. without going to any pyrite resource. You can simply use the author resource to download the PDF, and then you can find all the additional information that you need on any of these topics. Okay. The algorithm that I have shown to you now is intended to maximize safety, okay, or at least to give you more opportunity for maneuvering around trajectory, right? So that you could meet your motion constraint more easily. But when motion algorithms were first developed, their first concern was shortest path. And so shortest path, you suppose you want to go from this to this, okay? You can start from this point, then move around the side, like this, grazing it, grazing it. Then move around this direction, around this direction, along this direction, again grazing this vertex, and then reach your destination. So in this case, the philosophy is quite the opposite of what we have seen. We don't want safety. We want to stay as close as possible to the obstacles if this is helpful. Because ideally, I would like to join these 2 points by a straight line. This would be the shortest path. I cannot make it. Okay, I have the obstacles in between, so I graze the obstacles and move along the periphery of the obstacles. Okay? But of course, I cannot penetrate inside the obstacles. And I try to do it to modify as little as possible the optimal line of sight connection, which of course here is not there, right? Because there are obstacles in between. So I want to depart from the shortest line as little as possible, moving around, okay, moving in very close proximity of the obstacles. Is it clear? So as I said, here we have turned our paradigm upside down, and we want to do exactly the opposite of what we wanted to do with Voronoi diagrams. How can we do this? Okay, first of all, we define reflex vertex. Oh. What is a reflex vertex? A reflex vertex is a vertex between two edges, okay? Between two edges, such that the angle, here I wrote the area, but it's wrong. Let's say the angle in the configuration free space is greater than pi. So what does it mean? Consider this case. Suppose I have a figure like this. This is a triangle, right? This is the obstacle, and this is the configuration free space. Okay, here, this angle is smaller than pi. Therefore, the angle outside, the angle that lies in the free space is greater than pi. So this point is a reflex vertex. Okay? You want to take a small break? Okay, I see that you are tired. Let's take a small break. Okay, so going back to this guy here. So as I said, a reflex vertex is a vertex such that the part of the angle that lies within the configuration free space is greater than pi. Okay. So if you have a convex polygon, this is not, this is a convex polygon, then all the vertices have necessarily to be reflex. If you take a non-convex polygon like this, then you can have vertices like this one, which is not reflex. Okay. Okay, the key point is that the graph is made of reflex vertices. Okay. And so how do we find this graph? Okay, first of all, you consider, first of all, you just have to search over all the reflex vertices. You list them all. And then we know the nodes of the graph, right? By simply listing all the reflex vertices, you've got the nodes of the graph. Okay? Then you need to find the edges. Okay, what are the edges? First of all, if you consider, if you have an edge of COPS that joins 2 points, then this corresponds also to an edge of the graph. Okay. So in this case, this is an edge of the graph. This is an edge of the graph. This is an edge of the graph. So all the sides of the obstacles, if they are convex. If they are not convex, no. But if they are convex, all the sides of the obstacle are part of the edges of the graph. Are edges of the graph. Okay. In addition, if you consider 2 other points like this, if there is a bitangent line, so you join these 2 points, if the line that joins the 2 points is tangent to both the obstacles that it crosses, then it's part of the graph, so it is an edge. Okay. So this means that this bitangent line should not poke into the interior of the obstacles, and this is clear, otherwise it wouldn't be tangent. Okay. Doesn't have, and the 2 vertices must be in line of sight. This is the definition of bitangent line. Okay. So if you consider 2 vertices that are in line of sight, okay, that do not enter into the interior of any obstacle, this is a candidate for a bitangent line. And if it's a bitangent line, then it's part of the graph. So this means that if you start, suppose you start from this, these dotted points, you see, are associated to, sorry, not this one. Yes, because if you consider this angle is greater than pi, so this is a vertex point. This is not, because if you see the angle that lies in the free space is smaller than pi. This is not. This is. This is. This is. This is. This is. These are not. These 2 are not, because as you can see, the angle is in the obs part is smaller than pi. This angle here is smaller than pi. Okay. This is, as I say, this is, and these are the points. Okay. Then this is an edge. This is an edge. This is an edge, and this is an edge. Then is this a bitangent line? It touches the 2 points. The 2 points. It doesn't poke into the obstacles, right? So it's a bitangent line. This is an edge. This is an edge, and so on and so forth. So this way, you construct your roadmap. Okay. And once you have your roadmap, then again, you are in the situation in which your queries can be made on the graph. Okay. Okay. Clearly, this approach is not the one that gives the greatest guarantees in terms of maneuverability around the trajectory, because here you are grazing the obstacle. If when you make the motion, you should make just a small circle around, you easily penetrate into the obstacle, right? Because you don't have room around the obstacles. By construction, try to stay to go straight and stay as close as possible, right? So for certain, this type of solution doesn't give much guarantee per se for the possibility of finding collision-free maneuvers. Okay, but again, you have the possibility to inflate the obstacles to gain sufficient margin for maneuver. Okay, clearly this is much easier in terms of algorithm to create a roadmap like this than to create a Voronoi diagram. Okay, it's much more computationally effective. Okay, ciao. So this solution here is something that can be taken into consideration because it's very for two reasons. One, as I said, is the most obvious, which you want to find the smallest possible routes, right? The shortest possible routes. And the other is because it has an amazing efficiency. It's really, really efficient. Okay, this being said, I would like to conclude this part on combinatorial approaches and say, okay, as I said, you have combinatorial approaches are all about converting the structure of your path planning problem into something which is discrete in nature, which is a navigation problem on graphs. You have to account for the problem that I say, that when you do actually you follow this course for real, you have to maneuver. And when you make the maneuver, if you don't have a sufficient margins around, on the side of your road, of your way, then you could, when you move to the real object, to the real robot, you could have bad surprises. But then, with these limitations in mind, you have three possibilities. One is to go for exact construction of cell-based decomposition, which can be made by trapezoids or by using vertical scan, or by triangles using radial scan. Or you can go for a solution that is approximate, like using quad trees. Okay, you split your space adaptively so that when you are far away from the obstacles, you use larger sides of the cells. Or you could consider a completely different approach, which is this generalized Voronoi diagrams that we have seen, that by construction produce the maximum clearance roadmap if you want to stay as far away as possible from the obstacles every time. Or, on the contrary, if you have the opposite goal, which is going for shortest path, then you can decide to graze your obstacle. But in this case, you take some risks, because when you have to maneuver around your trajectory, you don't have much space. And this summarizes all we have seen on cell-based decomposition. Okay? All of these approaches are well supported by libraries, as I said. So you can use whatever library you want, but repeat once again, I want whatever choice you make to be well justified and supported by also a comparison with other approaches. And I want you to show me to be knowledgeable with the other options and that you chose a given approach and a given supporting library, etc., because you did it based on the fact that you didn't pick one just because I said, okay, in my opinion, this is the easiest to use. And no, this is not sufficient to me. Okay, good. This said, we can move to another topic, completely different approach. In this completely different approach, I can start it. It's the sampling-based approach. Okay. What is this sampling-based approach? It's a way to avoid having to meddle too much with geometry, right? And instead of thinking about the shapes that you want to use, etc., what you do here is to do something much simpler. You start, you start extracting points randomly. Okay, I don't think I uploaded these slides. I didn't, right? So maybe you need the slides to take the notes on, or I can just go on. Okay, so give me a few seconds. Give me a few seconds and I will solve the issue. Okay, so the idea there is simple. You start making an extraction of samples. This is configuration space sampling. Then what you try to do, okay, suppose you have obstacles in the middle here, is to connect every time you create a new sample to connect it, and you try to verify if there is a viable connection. Okay, in this case there is. If you try to connect this, there is not. Okay, so if we extract at this point, we wouldn't be connecting it. And to do so, you use the geometric models that tell you, as before, if a line intersects the obstacle or not. And then you keep going, creating your samples until you create again a roadmap. Once you have the roadmap, you can proceed with discrete search, as we did before. So once again, we try to reduce the problem of continuous motion into a simple problem, which is discrete navigation of a graph or of a tree. Yes?
To find the nodes from starting to the ending point, can we also use like RRT star?
Yeah. Indeed. The RRT star is something that we will see later on, is one of the possibilities. These sampling-based methods are a larger category of methods. And RRT star or A star is one of the representatives of this class. Okay. But we will see it later on. So let's say that one of the advantages of using this approach is that whatever happens here and whatever happens here can be decoupled, right? You can think of the collision detection as an externally provided black box, and you can simply have your algorithm that performs the sampling of the space and then exploits the services of these external components. Okay? So, generally speaking, all the methods that fall in this category are work as pretty much as this. You initialize an empty graph, then you sample a random configuration. If this random configuration is so you start you have your space in which you want to move, you have your initial position, you sample a point. If this point is in the C-free space, you take it, otherwise you keep extracting a new one. Then you try to see what are the nearest neighbor to the point you just extracted. Okay, in this case, there is just this. And you see if it's possible to connect them by using an edge that does not collide against any obstacle. Then you keep sampling another point, suppose this, and then you try and see what is the closest edge, sorry, the closest node, and then you try to see if it's possible to make this connection, and so on and so forth, right? So that's pretty much the way it works. So it's embarrassingly simple in the idea. You keep extracting new points, and then you try to see if it's possible to connect them. Again, this work can be done on a purely geometric basis. You can search for polylines again, and then postpone the problem of interpolating your polyline to a later moment. Or you can directly consider the kinematic structure of your robot, and then once you extract samples, you are working in a higher dimensional space. In this case, you are also considering the orientation, for instance, and then you try and see if it's possible to do the connection directly with a maneuver. Okay. Okay, so essentially in this approach, we have got two components. One is sampling, and the other is a collision detector. Okay, so sampling samples configuration in C. Usually you draw samples uniformly with different strategies. So typically you just pick up points randomly using a uniform distribution. But you could also have different ad hoc strategies for specific types of problems, right? For instance, a few years back, we have dealt with a problem of motion planning of a robotic car along a path. So in this case, we started from the track, okay? And we found it convenient to split the track into several way lines, and then we picked up the samples along these way lines. So sometimes the structure of the problem can suggest an ad hoc strategy, okay? But typically a good solution, if you don't have any prior structure of the problem, is to sample randomly. Okay. Now, what are the components of any sampling-based algorithm? Essentially two. One is the nearest neighbor. Okay, so you extract a point, you want to find the points in your set, which is the closest to any other to your point, the point that you have just extracted. So this is of course a nightmarish effort if you keep scanning for the entire set of points every time. So you need to do something smart. And this thing, this smart thing is typically using specific spatial data structures that are called the KD trees. Okay. KD trees are the trees that allow you to find the K closest points within a B maximum distance from you. And you can use this tree-like structure to have a very efficient management of this problem. Then you have another aspect. Once you extract 2 points, how do you plan a trajectory that joins them? Okay, if these 2 points are, as I said, you work in a geometric fashion, you simply connect them through a polyline. But if your point is something more complex, you want to consider also the orientation of the vehicle. So it's a point in 3D actually. You want to plan perhaps the best trajectory that knows this. So the local planning that joins 2 points needs not necessarily be this, but it can be already something more sophisticated. Okay, then you can say, but why don't? Okay, here there are some pros and some cons. Okay, if you create your interconnection on a geometric basis, then you decide your optimal path using Dijkstra or Dijkstra or whatever, and then you interpolate by using multi-point Dubins or any other interpolation algorithm, and then you follow the interpolated line. What you have is that when you construct this structure, the construction is easy because you simply extract point and see if your line intersects some obstacles. But then parts of the difficulty is shifted to a later moment. Because, okay, first of all, you have to do this interpolation, but secondly, most importantly, if you find that at that point that there is some collision, you have to backtrack and consider other options. Okay, because if you suppose you have, okay, you consider this type of structure here, then you say, okay, this is my shortest path. Then when you try to do your interpolation, you find that actually this is the trajectory that you follow. I crash here. What do you do at that point? You have somehow to backtrack, perhaps changing this point, choosing a less convenient one, or perhaps try to reshape this trajectory by choosing an intermediate point along this interconnection in order to avoid the collision. You have to do other things. You have to go back to your decision. Okay. So if you make the search already considering a local planner that accounts for the kinematic of the vehicle, you have no surprises afterwards. Okay, you can always have surprises, but just if the obstacle is greater than you expected, if your perception makes errors, or you can have other types of exception. But assuming that your information is 100% reliable, if you consider during the planning phase the kinematics of your problem, of your robot, then you will not have a surprise later. Okay, but if you don't consider it, it's much quicker to construct this plan. Okay, but then you may have to reconsider some choices to do backtracking if you find conditions like this. Okay, is it clear? And this is one of the trade-offs that you will have to explore. Right. So if you go for a solution or the other, I would like to have evidence of why you chose one or the other. Some quick test on a small scale example that gives you, okay, given what problem, it's better to go geometrically and then fix things up later, or the other way around, right? Okay, but now let's go to a more, let's say, conceptual, theoretical problem. And this problem has to do with the very notion of sampling. Okay, why? Because here we are in a situation in which C, the configuration space that you want to sample, is uncountably infinite. You know what it means to something which is uncountably infinite or countably infinite? All of you know it? No. Okay, good. Okay, if you consider, let's say, the natural numbers, 0, 1, 2, 3, and so on and so forth, they are infinite, okay? But they are countable. What does it mean? That you can count. This is the number 1, this is the number 2, this is the number 3, you can count them, okay? If you consider points, like in Q, okay, which is the set of rational numbers, which is given by the ratio of two numbers. Since the ratio of two numbers, okay, there are better ways of saying it, but you can understand that here, if the numerator and the denominator are both countable, somehow you can find an algorithm to count all the possible rational numbers. If you consider something which is this is the diagonal of a square. So it's a square root of 2. If this is 1 and this is 1. Pythagoras is shown back, okay, let's say 2,000 years ago, even more. I would say 2,500 years ago, that this number is not countable. You cannot express it as any fraction. Okay? And how do you distinguish a countable from an uncountable number? If you consider any fraction, you can have something like 10.9, 9, 8, 3, 2, 1, etc. But then at some point, you will repeat again the same sequence, right? And this is called periodic. Okay, whatever fraction you can imagine, you can always find a repetition of the, you can have either a finite fractional part or a periodic repetition of a non-fractional part. Okay, so it can be 100 digits, but then at some point it repeats itself. And so it's countable. If you consider square root 2 or logarithm of 3 or exponential of 5, you can see that you can express it again as an integral part, comma, then some digits, but these digits never repeat themselves in any way, right? You will have, the more digits you find, the more new pattern will emerge. You will never have something that repeats itself periodically. And then you say, okay, this is a nice, intriguing questions for mathematician. No, this is a strong implication for us because we are working with computers, and computers are inherently countable machines because they are made of a finite number of 0, 1 digits, right? And so we have two problems. First, we have a limited amount of memory. We cannot express an infinite number of digits. Okay, number one. Number two, even if we add an infinite number of digits, inherently the computer is made in a way that needs this type of regularity. So this is to say that countably infinite, countable infinite is for us much better than uncountable infinite. Uncountable infinite is the real nightmare, okay? It's the real nightmare, but it's life. Because life is made like this. I will have also square root of 2 when I draw any figure here. But this means that when we deal with geometry in computers, we are inevitably making approximations. Even if I had a very large number of digits, I would inevitably making approximation because I would approximate the real number with the rational numbers. Okay. Okay, so going back to the problem here is that planning happens in the free physical space, and so the configuration space is obviously uncountably infinite. So it contains an infinite number of configurations. It's not even countable. Okay, whatever planning algorithms I can choose can only deal with a finite and typically small, relatively speaking, number of samples. So this means that the sampling strategy becomes important, okay? Because if I make a sampling strategy, only a subset of this infinite samples will actually be used. So, because many of the points that I will sample will be useless. So I need a sampling strategy that combines two effects. On the one hand, it covers as much as possible the environment. On the other, it makes a good use of the few samples that I can extract. So it has to be effective in covering as much space as possible, but it also has to be efficient in trying to waste too many samples that are not going to be used, right? So the sampling strategy is actually key. Okay, now I would like to, before moving to this, there is another conceptual point. Okay. We would like, taking any point A and any point B, I would like the guarantee that by choosing an arbitrary number of points, eventually I reach B from A. This is impossible. This is impossible because C is uncountable. Okay, so it's very much possible that the 2 points will be a square root of 3, 1 from the other, right, in strange combination. So by the very limitation of my computer, I cannot reach exactly that point. I cannot even generate that point. So how can I be supposed to reach it? Okay? Is it clear? Okay? There are some points which are exactly reachable, other points in the configuration space that by the very way this construction is defined are not reachable. Okay. Now, this is the bad news. The good news is that it's true. I cannot reach that point, but I can reach a point, I can extract a sample, which is arbitrarily close to that point. Okay? So, suppose I want to go from 0 to square root of 2. Okay? Okay? I cannot reach square root of 2. Why? Because I should make some steps that are countably finite. Okay? Or infinite. But anyway, countable. So my computer is only able to move with some type of discrete steps like this. So I can never reach this point, but if you give me enough time, enough digits, enough computing power, I can take to a point that is arbitrarily close to this point. Okay? So in other words, if I take a real number, like square root of 2 or like logarithm of 4, a logarithm of 4, okay, depends on the basis of the logarithm. Let's say square root of 2 cannot be generated by any computer, So I cannot reach that point, but I have an infinite number of rational points that are as close as I want to this point. Is it clear? This is a subtle point. And this has to do with the notion of density. Okay? What does it mean? First of all, I give you the definition, and then I try to explain why this definition is relevant. If I take a set U, I will say that it is dense in V if its closure is equal to V. Okay? So what is its closure? The closure are the boundary points. Okay, the frontier of the set. So if you take an open interval from 0 to 1, okay, this is an open interval, meaning x strictly greater than 0 and strictly smaller than 1. Okay, it doesn't include 0 and 1, right? The closure of this set, if this is the set U, the closure of this set is 0, 1. That is all the internal point plus these two frontier points. So the closure of this set becomes x greater than or equal to 0, smaller than or equal to 1. So it means it's the internal part of the segment plus the two boundary points. This is the closure. Okay? Okay? Now, it's a little bit complicated to show, but if you take the rational numbers are the one that can be expressed as m over n, with m and n integers. The closure of the rational numbers are the real numbers. Okay? Okay? So this means that I cannot reach exactly any real number by moving along the rational number, but can get arbitrarily close because there is always a real number which is my frontier. Okay, it's a long story, but this is the intuition. Okay, I don't want to bore you to death with interesting mathematical details on the theory of numbers. Okay. Now, what does it mean density for us? Density for us means that a random sequence, if I take a random sequence, the random sequence is dense with probability 1. Okay, so suppose you take rand 1, 0, 1. That generates a number in the range from 0 to 1. Okay, so this guy generates a number with uniform probability. In fact, you know that this is not a real random number; it's a pseudo-random number because I have the seed, etc., etc. But forget about it. Suppose that we had a true random generator in our PC. Then this sequence of numbers, if you consider a long sequence of number like this sequence of number is dense with respect to the 0, 1 segment. What does it mean? That if you keep extracting enough sampling, enough samples, you can get arbitrarily close to any point of the segment. Okay? With probability 1. And there is another interesting fact. With probability 1, what does it mean with probability 1? So suppose I tell you two things. One is I am 100% sure that if I do like this, I will take the pen. 100% sure, it means I will always take the pen. Or if I tell you, I will take the pen with probability 1. Am I saying the same thing or not? in your opinion, I am saying the same thing or not? Yes. Who says yes? The two of you? The three of you? Who says no? Okay, and why?
You are saying that I'm sure 100%, not
A probability one. Yes. Okay. So you just guessed.
No, I mean, maybe you don't get it right.
No, the question is like this. If I say I will cover densely this segment with probability one, it means that if it could happen that, okay, in this case, my event space is made by the sequence of number that I extract. Okay? It's possible that I will always extract this number for a very long number of time. No? This number is 0.2. It's possible that I keep extracting 0.2, 0.2, 0.2, 0.2, etc., forever. But what is the probability that this will happen? It's 0, right? So it's an event that is possible, but the probability that it will happen is 0. Okay? It means that for all the life of the universe, it's possible that sometimes I start extracting random samples and I always sample the same damn number. But the probability that this will happen is extremely low, or 0. Okay? So when I say I'm almost sure, or that I'm sure with probability 1, I'm not saying that I am really sure. I can bet whatever sum you want on this, right? Let's make an example, right? Suppose you toss a coin, and this coin has 0.5% of giving head and 0.5% of giving tail. Okay? Okay. What is the probability that in a number of n extraction, I will never get tail? Yes? Okay, if I take 0.5 once, it means that I have extracted my thing, I can take head, right? Then suppose that I take head again, head again, head again, okay? So the probability that I will get n heads in a row is 0.5 to the power of n, right? Okay. So the probability that I will get at least one tail is 1 minus this. 1 minus this is the probability that I will get at least once a tail. Tail. Then suppose that I say with probability 1, I will have at least, with probability 1, I will have over an infinite number of extraction at least one time tail. Okay? This is, of course, 1 minus 0.5 to the power of n. If you make n become large enough, this 0.5 will shrink. So if you make n go to infinity, it will become 1. So it's true with probability 1 that I will get at least once my tail. Okay, but still, it could be possible that in one execution, I will take head forever. Nothing prevents this. There is no physical impediment to the fact that I will always take head forever and ever. Okay? So saying that something will happen, surely, is not the same as saying that it will happen with probability 1. Is it clear? Clear or not? Okay. So the nice thing is that if I take a number and I extract with uniform probability a real number in a segment, whatever point I will take in this segment as a reference, sooner or later, I will take a point which is arbitrarily close to this. Okay? If you take, I want to be closer than 1 part over a billion. Okay? If I extract a long enough sequence, I will get a point in which I'm closer than 1 part over a billion. It can also be computed how long this sequence should be in order to have at least a guaranteed probability. Okay? So it means that if I go for uniform sampling, I will cover densely the entire segment with probability 1. So it means that if I want to cover, for instance, a square or a cube, I have to do the Cartesian product of 3 uniform variables. You extract uniformly along x, uniform along y, uniform along z. And if you do this, you will get arbitrarily close to any, with a long enough sequence, to any point in your space. You understand that this for us is a key fact, because if we extract randomly, I want to be sure that sooner or later I will get close enough to the goal. Otherwise, it's ill-posed. It will be ill-founded, right? I want to make sure that for a long enough sequence, whatever my destination is, I will get arbitrarily close to this destination. And this is guaranteed by uniform sampling. Is it clear? Okay, for today we can stop here.